So we're going to kind of blend section 1.1 and section 1.2. I've already mentioned a few things about statistics. There's really two parts to statistics. There's the descriptive part, where you take a huge data set and you try and describe it and summarize it in some way, because just the gargantuan amount of numbers that are available to us are just too much to try and look at and draw conclusions of unless you do something ahead of time to whittle it down or summarize it. So that's, like I said, the descriptive part of statistics. And then we're going to go on and try and make conclusions, generalizations going beyond our statistics, try and make forecasts, etc. So in front of you, you should have a handout with some definitions. Throughout today, we're going to go through this and discuss a bunch of these things. Some of them won't be discussed until we get into chapter 3, particularly the measures of variation. But section 1.2 talks about statistical and critical thinking. One thing that's important with statistics is to try and understand if there's going to be any kind of conflict of interest of a person doing a study and the person, or in the results they're trying to come up with. Particularly, let's take a look at problem number 8. Get this up here. It says an article in the Journal of Nutrition noted that chocolate is rich in flavonoids. Hey, that's good news, right? We should all eat as much chocolate as we want. The article notes that regular consumption of foods rich in flavonoids may reduce the risk of coronary heart disease. Wow, is it saying like we should like eat a box of M&Ms every day? You know, have a healthy heart? The study received funding from the Mars Incorporated Candy Company and the Chocolate Manufacturers Association. Does anyone see maybe a little conflict of interest here? Maybe, you know, hey guys, here's some money, go do research and, you know, find conclusions that match what we would want. So one of the things that the author would ask you to do is be conscious of that. Look at the data and try and understand, do the people doing the study have some kind of a conflict of interest here? More in the way of statistical thinking. There's a difference between correlation and causation, and let's take a look at that with respect to problem number 4. It says, what is meant by the statement correlation does not imply causation? Correlation means that two things kind of go together, like studying hard and good grades. They tend to go together. But causation is something different. Smoking causes lung cancer. Now, there's a nice correlation between obesity rates and how much television you watch. That's a correlation. The more TV you watch, the heavier you tend to weigh. But is that a causation? Does watching TV cause you to be overweight? No. What causes you to be overweight? It means you don't exercise enough, or you're eating, you know, a quart of Ben & Jerry's as you watch the Late Show. You know, that's the problem. You're consuming more calories than you're burning. So I'm hoping you see the difference between correlation and causation. A lot of times these two things get confused. Let's turn over to problem number 28 then. It says, in the years following the end of World War II, it was found that there was a strong correlation or association between the number of human births and the stork population. It therefore follows that storks cause babies. What do you think? Storks cause babies? I don't think so. So what it's getting at again is the difference between correlation and causation. One is not the other. Another problem that you have with a lot of data is something called a voluntary response. And the definition for that's on page 7. So let's look back there, page 7. Voluntary response. Voluntary response sample or self-selected sample is one in which the respondents themselves decide whether or not to be included. So there's a problem with that. If the respondent is deciding, yeah, I want to be a part of this, then they might not necessarily be representative of a population anymore. They might be a little bit more motivated in one way or another, and it's tough to draw inferential statistics from a set of data that's collected with this voluntary response. Let's take a look at problem number 10. There. This is in a survey of 109 subjects. Each was asked to indicate how many text messages they send and receive each day. The sample consisted of those who chose to respond to the request posted on StatCrunch website. Does that sound like a self-selected sample? Well, in my opinion, the answer would be yes. If you're surfing some website and you see a request to take a survey, then yeah, you're choosing to be in there. You also happen to be cruising by that website. It's difficult to try and generalize that to a larger population, maybe all students or students at community colleges or people in the U.S., etc. So you have to be careful with data that's based on a self-selected basis. We saw problems like that. In fact, I used to have to go back to, there was an election between Truman and Dewey, in which the statistics were poorly done, and there's a famous picture of President Truman holding up a newspaper, the Chicago Tribune, saying, "Dewey wins." Well, it was big egg on the face for the Chicago Tribune because Dewey didn't win. But part of their problem was that they didn't do a good job collecting their statistics. And if you don't have good data to begin with, then it's hard to make generalizations from there. Might talk about that later. Certainly, we got a more modern example, the last election, and again, that's something we can talk about. Now, sometimes statistically, you can find a difference between a couple things, but let's take a look at problem number 14 and have you tell me what you think of the difference. This is in a study of the gender aid method of gender selection. 1,000 users of the method gave birth to 540 boys and 460 girls. There's about a 1% chance that such an extreme result would occur if the method had no effect. So, okay, what's the usual odds of a boy or a girl? How many would you expect out of 1,000 to be boys or girls? 500, right? And you expect a little bit more, a little bit less, just by luck, all right? You're not going to get exactly 500 very often. But 40 more than what we expect is rather unlikely. So what this is saying is that it seems like the method is working because you got a lot more boys than you would have expected. Now that's a statistical significance. But on a practical level, 540 boys, that's only about 4% more than you would expect normally. How much money are you going to spend to increase your chances of having a boy or a girl by 4%? Is that worth a lot to you? I don't know, I guess it depends on how desperate you are for one gender or another, but 4% doesn't sound like a very, big difference to me. So it's statistically significant, but practically, well, it doesn't seem like it's really making a big practical impact there. Now what I'm doing is I'm working through a bunch of problems. I tend to work on the even problems that are in the book, and then I'll assign some of the odd problems at home. Let's continue with problem number 18. It says, the listed pulse rates were obtained for the third National Health and Nutrition Examination Survey conducted by the U.S. Department of Health and Human Services, National Center for Health Statistics. Is the source of the data likely to be unbiased? Would you trust this data more than you would data funded by the M&M Mars company? Probably. You know, at some point or another, you know, you're going to have to say you trust or not, don't trust the data. And in this case, I don't see really much reason for the researchers to be biased one way or another. They're government researchers. So we'd hope so. Now, I think I sent out an email that a lot of you got. You brought your laptops today. That's good. We will get around to using those. But before we do that, if you have a graphing calculator, or if not, take out your phone. I don't think we'll need anything quite so fancy, but one of the coolest things that I picked up about my phone was that when you go to calculator, if you want something a little more sophisticated, and you turn it, come on, there you go. You get more of a scientific calculator. So if you need some high-tech stuff, then it's there. But let's look at problem number 32 and work on some percentages and just a little bit of arithmetic. This is not a course in math. It's much different than a math class. In a math class, you prove things with certainty. In a stat class, you say, well, we're pretty sure. We don't have the certainty of our conclusions that we do in a math class. But here is a little bit of math for us in problem number 32. So in a Harris poll of 2,513 adults, 76% say they'd prefer $1 to be in the form of paper currency. So the question is, what is the exact value of 76% of 2513? So let's take a look at that. 76% of 2513. Well, we could rewrite this. 76% as a decimal is 0.76. The word of means times. So 0.76 times 2513. 1909.88. So do you think it's likely that of this poll of 2,513 adults that 1,909.88 of them said they'd be in favor of a dollar to remain as their paper currency? Is there a problem with this? Yeah, I don't want people cutting me up. I mean, I like 100% of me, not 88% of me. So, yeah, most likely the result was 1,910. And if you want to, you can check that. Take 1910 and divide it by 2513, and we get something that rounds to 76%. So there we go. I think we probably also answered part B. Could the result from part A be the actual number who said they prefer $1 to be in the form of paper currency? No, it couldn't. What is the actual number of adults who said they prefer $1 to be in the form of paper currency? The 1910. Let's take a look at one last part here. Part D. Among the 2,513 respondents, 327 of them said they prefer a dollar to be in the form of a coin. What percentage of the respondents who said they prefer a dollar to be currency in the form of a coin? So how are we going to figure out what percentage that is? Yeah, divide. So for part D here, we're going to take 327 divided by 2513. And then if you want, you can take that result and multiply it by 100. Moving the decimal over 2 places to the right, we'll do the same thing. So 327 divided by 2513 times 100. So for rounding it to the nearest percentage, it'd be about 13%. About 13% of people want a coin for the dollar as opposed to paper. Let's do one last one in the form of critical thinking. In an ad for the club, a device used to discourage car thefts, it was stated that the club reduces your odds of car theft by 400%. Is anything wrong with that? What's the most that you could decrease something? 100%, yeah. You can't decrease it more than 100%. Once you've decreased it 100%, there's nothing left. So, yeah, that one's a little bit off. Somebody in the ad department needs to take a math class, preferably stats. Okay, so kind of a quick overview of a few issues you can run into statistics. We're going to start working with more of the terminology and work towards summarizing things in chapter 2. But is there anything here that we went over that you're a little unsure of? Would like to follow up with a question? All right. If that's the case, then let's stop and call it a day on this one. For homework in this section, try 1 through 33, just the odds.